so much, Emma. That was really important research I'm glad we got to hear about. Next up, we have Timothy Grabowski, presentation titled Using Citizen Science to Model and Multi-Season Dynamic Occupancy Models to Evaluate Surgeonfish Abundance Patterns.
Well, thank you everybody for hanging out to the end here. I know that this sounds suspiciously like I'm going to get up and talk about math today. I promise that it's going to be, I'll keep that to a minimum. I'd like to acknowledge all my co-authors, in particular my colleague Jim Peterson at Oregon State for help with this work. So a little background, surgeonfishes, the family Acanthuridae, they help maintain coral reef health through their herbivorous nature. They eat a lot of algae, keep that algal biomass cropped down on coral reefs, but they also support a lot of commercial and non-commercial fisheries throughout the tropics. Maintaining surgeonfish populations has become a priority of management efforts for fish here in Hawaii. If you pay attention to the news at all, you might have heard about the herbivore management rules that have recently gone into place by DAR, the closure of the Kui fishery in West Hawaii. So surgeonfishes are making the news, and not necessarily as good news. There's a lot of factors that influence surgeonfish abundance at large spatial and temporal scales, and we really don't understand those particularly well. And ultimately, this lack of understanding sort of becomes a hindrance to effective management. So developing this understanding is going to require expanding the sorts of data that we look at in order to answer these questions. Scientific dive survey protocols are great, but they rarely include repeat visits to sites. Most agencies are trying to collect data from a breadth of sites rather than focusing on specific sites with repeat visits. Scientific surveys that do repeat revisits to a site are usually relatively small scale as well. Not a lot of sites revisited. And data tracking large-scale environmental variability in Hawaiian nearshore waters are severely lacking, to be honest. However, there's large amounts of data that is routinely annually collected by citizen scientists worldwide. The one that we worked with for this study was collected by REEF, or the Reef Environmental Education Foundation, which I know some of you in marine science or involved with the MOP program might be represented in this data set with your efforts. REEF is like the National Audubon Society for fishes. They do annual fish counts with recreational divers. The divers perform roving surveys, and they identify all the fish they see during their dive and assign them to a categorical abundance scale. For Hawaii, what this means is we have access to over 20,000 surveys at 500 plus locations statewide. And this data set has been ongoing from 2000. And the beauty of it is that most recreational dive activity in the state is concentrated at particular locations. So repeat visits are very common. Now, there's some issues with it. First of all, you have to trust that these citizen science divers are identifying the fish properly. But also the surveys are not nearly so standardized as what we do as scientists. Sometimes there's questions about where the surveys were actually conducted. For the purposes of this study, when we got the GPS locations of survey sites, basically we drew a 100-meter radius around that location, and that was the survey site for that particular study. We use these data to build multi-season, multi-state dynamic occupancy models. What this means is we're predicting occupancy, or the probability that if you jump in the water at one of these dive sites, what's the probability that you're going to see the species of interest? Okay? The multi-state aspect of it means that we have two levels of abundance. We have so three categories. The fish can be absent, that you can jump in the water and the fish is present, or you can jump in the water and what's the probability of you going, holy crap, there's a lot of these things here. Okay, so that's the technical term, but we just call it present and abundant for the, the not so technical. The multi-season, we're treating each year as a survey season, so we're making assumptions about the population being sort of closed during the year. And then on New Year's Eve, there's this wild festival where mortality, recruitment, and all those things in the population happen. This is a simplifying assumption of the model. Most population models do this sort of assumptions. We got to start somewhere. So what this looks like is if we have 3 locations here in our first season. Site 1 is an initial status where the population is occupied and abundant. Site 2, occupied. Site 3, not occupied at all. There's a probability of each of these 3 outcomes changing over the course of, for the next season, the next year when you jump in the water. And then the following year, there's the same set of probabilities. And so we're interested in estimating not only what the probability of there being the fish present in that square at the beginning of the study, but what's the probability that there's a change in the occupancy state? Meaning it goes from fish being there to not being there. Whether they're there or there are a lot of them. We're just interested if their presence or absence has changed. And that's this psi. R is a change in abundance. Are we interested in their change in their numbers in the square? And then detection probability. What's the probability of us jumping in the water, the fish being there, and us seeing it and recording it as being present? And so the model is doing all of these things. And if there's enough interest, please come see me. I've been thinking about trying to develop a class in occupancy modeling. And I'm just not sure if there's enough interest in it or not. So if you're interested, come talk to me sometime. Anyhow, these are the 5 species that we're looking at. We have the kui, the white-cheeked surgeonfish, kole, ma'i'i, and manini. 4 of these fish, or 3 of these species are heavily fished. The kole, the manini, and the kui. White-cheeked surgeonfish was occasionally caught in the aquarium collection industry. It's not really targeted a lot in fisheries. And ma'i'i is sort of our control. It's not fished for in any significant amount. We use a bunch of existing data sets as covariates on our model. We mostly got it from ocean tipping points. We had substrate composition, bathymetry, effluent, reef fish landings, sedimentation, wave power, coral bleaching index, and ornamental aquarium landings all went into the model as factors affecting these probabilities. And then reef data, the divers provided us the covariates we used to estimate how they affected detection. So how long when the divers were down, what depth they were at, all those sorts of things. Not going to go into the math. I promise not to go into math. The global model was the top performing model for all 5 species, which means we probably need more data. As it relates to occupancy, substrate composition, slope, depth, and wave energy tended to describe occupancy and abundance patterns for these 5 species. So along the top here, this is just occupancy, and then the probability of jumping in the water and there being a lot of these individuals in there. And for each factor, the covariates had a different positive or negative effect and different strengths. And what it looks like is the darker the blue is here in each of these little squares, the more likely it is that they are present in these little squares, 100 by 100 square meters. And likewise, the darker the colors here, the more likely they are to be present and abundant. The reason why the more common species of manini and ma'i'i are not very abundant is that they have a higher threshold of being abundant. Probability of colonization, so going into the water, finding an empty site 1 year and coming back and finding the fish in there the next year, it's relatively low for all these species, but really low for kui and white-cheeked surgeonfish. In general, though, if they're present, they tend to stay there. There's a high persistence, relatively high persistence, with no more than about a 5 to 10% chance of extinction in a given year. Unfortunately, all these covariates are fairly static in time. They are snapshots. And so when we go to model that out, it looks pretty uniform across space. There's a low probability of these species becoming abundant at any given site in a given year, but generally speaking, if they are abundant somewhere, they tend to stay that way. And detection probability was surprisingly low, and tended to be most influenced by the amount of time that the divers spent down on the bottom looking for these fish. So this effort scratches the surface, but starts as a solid foundation for some other questions that we want to ask. So in general, surgeonfish species differ in their resiliency, and some of the species that we're most concerned about seem to be the ones that are least resilient. These data in general, the covariates were not as strong of an influence as expected, but as mentioned, these large-scale data sets that we have available to put in these models don't track through time. So you're looking at a changing a dependent variable and a constant independent variable, which makes it really hard to model. The citizen science data set offers a lot of potential to augment existing scientific surveys. And right now we're working on integrating scientific surveys into this model structure so that they can inform each other. And so with that, lots of people to thank for their help with this. And if I've got time, I'm happy to take any questions. Thank you. See, I promised no math.
Just curious about the citizen science versus scientific studies. Did you see any significant differences between those?
We have not plugged the scientific surveys into these models yet. So the reason why the repeat visits, I don't have time to go into all of that, but the reason those repeat visits are so important is because if you go down on a scientific diving survey and you report that species as being absent when it actually was present, you just missed it for whatever reason, that really tends to bias your estimates when you're trying to estimate biomass and distribution. And so those repeat visits lets you estimate that detection probability. It lets you assign a probability of that zero being a true zero and correct your estimates accordingly. Without that p-value, the scientific surveys run the risk of being really biased, particularly for less abundant species. But even for abundant species, if you're trying to count them, that detection probability comes into play in your estimates of the numbers as well. So it's an important concept that we really we're behind the terrestrial folks in this regard. They've been doing detection probabilities for years in their surveys, and fisheries is just starting to catch up with that.
Yeah, Tim, I wanted to ask if there was this is a related question, if there was a verification process already built into reef. So other iNaturalist or eBird systems, if something is implausible, it'll be flagged.
Yeah.
So if someone says there's a whale shark in Hilo One, that would be, flagged and that would be disregarded or thrown out data.
They have that in the reef data set. One of the reasons we wanted to work with surgeonfish is that if you look at these 5 species, they're fairly distinct from each other, coloration-wise, fairly visually distinct. I would be less confident in these results with something like parrotfish, which are very similar, and even sometimes experts have a hard time in the field distinguishing them. And I would not trust them at all for something like the different species of the nui nui that we have, which even experts can't reliably identify the species in the field all the time with 100% accuracy. So it does go through extensive quality assurance, quality control process at reef where they do biogeographical checks like that and some other things. There's usually training associated with it for lots of different places. I don't know if they do it in Hawaii. But we intentionally focused on species that also were visually distinct, a group that's fairly visually distinct from each other.
I'm curious if there was any surveys done during COVID to kind of compare the confounding factor of visitors as far as presence and absence.
So this data set, I believe, these models were run with data through 2020, end of 2020, maybe 2021. So it would include some period of time during COVID and some post-COVID as well. But I would have to double check that, because we've run a couple of iterations, but I think the most recent iteration has up to 2021 in it. Well, thank you, and thank you everybody for that. That was the last one.
Thank you so much for joining us for the 14th Annual Tropical Conservation Biology and Environmental Science Symposium. That concludes our oral presentations for today, so give a round of applause to all our presentations. Our silent auction is still open and it will close tomorrow at 3:15, so put in your bids, please. We have a lot of amazing items, and we will be moving into our poster room, which is in Campus Center 306, across the hall through those other glass doors and on your left. So you can join us there. We'll see you again tomorrow for any more talks. Thank you.
Hey. Nice to meet you, Isabella. Okay.